Okay, I'm recording now. Now we are talking about the degree of freedom analysis of mechanisms, trying to find out the degrees of freedom. And we said that the space, three-dimensional space, has 6 degrees of freedom, 3 being translations, 3 being rotations. And we said that the 2 degree of freedom 2 degree of freedom space has planar space, that is, has 3 degrees of freedom. That is, an object in 2-dimensional space has 3 degrees of freedom, x, y, and theta coordinates. In order to describe the motion of a rigid body in the 2-dimensional space, we need 3 degrees of freedom. So if you have a mechanism that has L links, there is 3 L degrees of freedom. That is, if you have 3 links with 3 degrees of freedom, in total you have 9 degrees of freedom. That's what this thing says. But the problem is there are joints, and the joints reduce the degree of freedom of the mechanism. There are the joints which are also called the kinematic pairs, and I tell you that these things are also called joints. Kinematic pair has another name, which is joint, by the way. I'm trying to write here, that's why. Okay, this will take some getting used to. Kinematic pair also means joint. There are the lower kinematic pair, lower kind of joints, which are and the higher joints. The lower joints are revolute, and prismatic are the more common ones. And there is the cylindrical joint, which is a 2 degree of freedom joint. In the cylindrical joint, there is 1 degree of freedom in this direction, moving back and forth, and also the rotational degree of freedom. But the ones that are very common are the R and P joints. Okay, I can write R and P joints are the ones that are most common. In 3 dimensions, there is the spherical joint that has 3 degrees of freedom. Helix has 1 degree of freedom. And the plane, which is seldomly used, has, we say, 3 degrees of freedom. Anyway, the most important ones are these cylindrical. These are the lower pairs, lower type of joints. Okay, the higher joints are rolling and sliding joints, rolling and no sliding joints. That is a contact. This is a rolling contact with no slip, in which case the degree of freedom is 1. But if there is a rolling contact with slip, the degree of freedom is 2. Then there are the gears and the cams. The gears have a degree of freedom of 2. The gear contact has a degree of freedom of 2. And there is, I will give you an example which will nicely illustrate why it is 2. But importantly, in between the gears, there is sliding motion, and the rotating motion is possible. That's why we have 2 degrees of freedom. In the belts and pulleys, we have 1 degree of freedom only, and the springs have no effect. And then we talk about the degree of joint, and we said that degree of joint has nothing to do with the degree of freedom of a joint. Degree of joint just shows how many links are connected to a joint. For example, a binary joint has 2 links connected. Ternary joint has 3 links connected, etc. Now, we talked about we came to here, the degree of freedom of a mechanism. Degree of freedom is the independent number of parameters required to define every link in the mechanism. For example, if you have a 4-bar mechanism, as I show here, in the 4-bar mechanism, if you just define this theta, you define the position of the mechanism. So in order to have this mechanism moving, you just need one motor to have it operating. Okay, that's the only necessary thing. Whereas if you have a 5-bar mechanism, you need 2 parameters to have it operating, 2 motors kind of, if you like, 2 motors at E and D if you want. So that has a degree of freedom of 2. We want to find out this from the analysis of mechanisms. That is the number we want to find it out from the number of links, number of joints, and the type of joints. Okay, so the degree of freedom of a mechanism depends on the degree of freedom of space, degree of freedom of the joints, and the number of the links and joints, and how those links and joints are distributed. But it does not depend on the shape or the size of the links, and also the springs that are in the mechanism, elastic elements, do not contribute to the mechanism's degree of freedom. So we define it as follows. Let's say that the lambda is the degree of freedom of space. L is the number of links. And by the way, this is important. This has to include the fixed link. That is, we always take ground as our fixed link. For example, if you have a 4-bar like this, in the 4-bar, we always take 1 as the ground, 2, 3, and 4. So this is why we call it a 4-bar. So there is a link here that is grounded, okay? So it includes, the L includes the fixed link. For example, the L here is 4. That's 4 here. J is the number of joints. F is the number of freedom of each joint. Fi should be, and the F is, the capital F is the degree of freedom of the total mechanism. And I gave you an example like this. If you have a 4 bars, 4 links, the total degree of freedom is 12. But if you connect joints to them, the degree of freedom gets to decrease. For example, if you have here, you have a cylinder in slot here, which reduces 1 degree of freedom. Here you have 2 revolute joints, rotary joints or revolute joints, which also decrease the degrees of freedom. So initially, the degree of freedom, which was 12, gets to decrease to 7 here. Now here you have, if these things are combined like this, you have 7 degrees of freedom. So just a second. This thing is unnecessary. The degree of freedom of a mechanism is simply the following. The degree of freedom of space, which is lambda, times L minus 1. Well, we always consider ground as link number 1. That's why we have L minus 1. Okay? Then the number of joints, lambda times j, plus the sigma fi, summation of the degree of freedom of each joint. Remember from the previous, how do we go to the previous one? Here. We said that if the joint freedom is degree of fi, then that joint constrains lambda times fi freedoms. So if you have j joints, lambda j minus fi freedoms are constrained by j joints. Okay, this is the number of constraints introduced by the joints. So therefore, what we have here is, let me see, degree of freedom without constraints is this thing, okay? And the number of constraints is corresponds to this, okay? L minus 1 simply comes from the fact that we are using ground as link 1. And this part comes from the previous page. It is explained in the previous page. So the degree of freedom of a mechanism is lambda, well, lambda j is taken into common parentheses, lambda L minus j minus 1 plus sigma fi, where I goes from, that's not written there, I goes from 1 to j. J is the number of links in the mechanism. So this is the general degree of freedom equation. And it is quite straightforward, actually. Lambda is the degree of freedom of space. Lambda is either 3 or lambda is 6. You just have to count the number of links. You just have to count the number of joints and find the degree of freedom of each joint. Well, let me give you an example, a very simple example here. Let's say that you have four links rather, not a 4 bar yet, but 4 links like this. Three links actually, as you see. But what is the degree of freedom of this first part? It can be described by, let's say, theta 1 here and theta 2. So this thing has a degree of freedom of 2, doesn't it? Whereas the other link, which is unconnected yet, can be described by this coordinate, let's say theta 3. So this has a degree of freedom of 1. So in total, let's say, f is equal to 3, as you see, right? 2 degrees of freedom on this side, 3 degrees of, sorry, 2 here, 1 here, total is 3. What if we somehow connect these two parts, this part and this part, put them inside with a revolute joint? What we will be doing will be decreasing 2 degrees of freedom, right? Because the revolute joint there would have a degree of freedom of 1, so it would be decreasing, it would be removing 2 degrees of freedom. So if the joint is connected, then f becomes 3 minus 2, it becomes a 1, which means that the degree of freedom of a 4-bar mechanism will be 1. I hope that is clear. This is understood. This is called the Grubler's equation, which says that the degree of freedom of the mechanism can be found from this expression we have. You just have to multiply with the degree of freedom of the space with L minus J plus minus 1, and then sum up the degree of freedom of each joint, in which each joint has a certain degree of, here again, we have I equals 1 to j. Okay. By the way, the degree of freedom of a mechanism, another name for the degree of freedom, you see it somewhere, is mobility. Mobility of a mechanism is another name for the degree of freedom. Okay, just remember this. So, any questions?
Hocam, is it possible to find the degree of freedom of the one who we found with this equation, hocam? Could you please solve it with this equation?
Is it possible to find what?
A degree of the freedom of what we have found in just a moment.
You mean the 4 bar?
Yeah, 3 bar. Sorry, 3 bar.
Yeah, it is called 4 bar. It is not 3 bar.
Sorry, 4 bar. Sorry.
It is 4 bar because the ground is a link also. Yeah, the next slide will do that. So just be patient a little bit, okay? I have it in the slides. Actually, I will solve many examples. Don't worry. We will be going through them one by one. Now, the degree of freedom, if it comes out that the degree of freedom is zero, or even in some cases you might get a negative number, okay, it is possible to do that. It means that you have a structure, okay? For example, if you have something like this, if you remember trusses in your statics class, okay, if you combine everything by revolute joints and so on, for example, if you find the degree of freedom of this thing, which is a truss, you will find that the degree of freedom of this thing is 0, which means that there is no motion here. So it is a structure. It doesn't move. Whatever input you connect to it, whatever motor you connect to it, you cannot move it because it's fixed. But if you have a mechanism like a 4 bar or a slider crank like this, for example, not a good drawing, but you understand, I hope. This is a mechanism now, and it moves. If you connect a crank to it, this has a degree of freedom of 1, so it is a mechanism. So there is motion associated with it. Or you might have things like robot arms, in which the degree of freedom is even more than 1. For example, one arm is here, another arm is here, another arm is here, let's say, with a gripper and so on. Let's say that this is a gripper. So this has a degree of freedom of 3, for example. Okay. So, but in general, in this course, we will be studying the systems with 1 degree of freedom most of the time. That is, you might get to analyze a system and find out the degree of freedom is 2 or 3. But in this course, we will be looking at the most important case is f equals 1. Okay, that is our will be our main concern. All the realistic mechanisms we will be studying in this course will have 1 degree of freedom. Okay, now to your question. Let's say that we have a 4 bar mechanism, as you see. The 4 bar mechanism has a fixed link, which is the ground 1. The input link is 2. The coupler link is 3, and the follower link is 4. And you have the number of links is 4. 1, 2, 3, 4. 1 includes ground also. J equals 4. Say, J means the number of joints. Let's see how many joints we have. One joint is here. Another joint is here. Another joint is here. It is very simple. It's just 4 revolute joints. You can say R, 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 R here. Okay. And each of those have a degree of freedom of 1. So we write our equation. 3 minus L minus J. Lambda is 3 here because we are in the plane. 3 minus L is 4. Number of links is 4. J is 4. Minus 1. Well, because it's grounded, minus 1 comes from that. Plus 4. So what do we have? 4 minus 4 is a 0. Minus 1. Minus 1 times 3 is minus 3 plus 4. Minus 3 plus 4 is 1. This is as expected, okay? As we have expected, the number of degrees of freedom of the 4-bar mechanism is simply 1. Okay? Our second famous mechanism is the slider crank mechanism. Again, you have 4 links, one including the ground, second link, third link, and fourth piston is the fourth link. The joints are 1, 2, 3 revolute joints. Plus there is a sliding joint between 1 and 4. Okay, so you have 3R. Let me see, how do I do that? Three R plus 1P is our joints. In which case, it is the same equation with the exact same parameters. Each of the joints have a degree of freedom of 1. So 3 times 4 minus 4 minus 1. This gives you a minus 3 plus 4. The degree of freedom is again 1, as you see. Okay. Just a second for the time being. What does it mean when somebody asked me privately? You don't have to ask privately, by the way. What does it mean when f is less than 0? Okay, let me explain that also. But I have to share the screen, I guess. So you have you see the PowerPoint presentation, right? I hope.
Yes, hocam.
Okay, we were here, but okay. When the degree of freedom is less than 0, you have a structure with extra constraints. For example, something like this would have a degree of freedom of less than 0. Well, this won't be this will be a 4-bar mechanism. But if you connect here and another link here, for example, this will be a box structure which has extra constraints, so that the degree of freedom, if you find it, probably it will be -1 here. Okay? That's what it means. It's a structure with extra constraints. Okay. Or statically indeterminate structure, if you like. So we have looked at the 4-bar and slider crank mechanisms. Let's look at another mechanism, which is a little bit more complicated. It has 8 links, actually. Again, we will find that the degree of freedom is 1. First of all, we start from ground, which is link 1. Then this is link 2, this arm. This is link 3. This is link 4. So you have a 4 bar here connected to a triangular link, which is 5. 6 is here, 7, and a slider. Okay. So the number of L is 8 here, as you can see. Now, the more tricky is to count the number of joints. You have 1, 2, 3 here. Here it's a multiple joint, which means that you have to count 2 joints here, okay? Because you connect not just 3 and 4, but for example, 4 and 5 here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and there is a prismatic joint 10. So J is 10. Okay. In which you have 9 revolute plus 1 prismatic joints. Okay. And each Fi for this thing is 1 because they are revolute and prismatic joints only. So if you, excuse me?
Hocam, so for the values of the joints, do we just add the degree of the joint?
Yes. Well, you just add, if, for example, if 2 links is connected to a revolute joint, the joint is called a single joint. But if you have 3 links is connected, then you have two joints there. So it is the number of links connected minus 1.
Thank you.
Okay.
Thank you.
So if you, yes, somebody raised the hand. Go ahead, please, Kashar. Yes, I'm listening if you have a question. Probably not then.
Hocam,
Yes.
For the degree of freedom of joint I for Fi,
Yes.
isn't the 8 joint has 2 degrees of freedom?
Which joint?
The 8 prismatic with plane.
No,
it is grounded.
No, it has 1 degree of freedom. You see, the prismatic joints always have 1 degree of freedom. You have to, oops, sorry, something happened. What you have to do is, when you draw a prismatic joint, you might draw it like this, if you like. But usually what you have to really do is something like this. You have to put 2 constraints on both sides. So this is not done here, but this is what you should have done. So it only allows a translation with respect to the ground. Do you understand?
Yes, hocam. Okay. And also, may I ask, we count all the ground links as 1, right?
Yes, that's true. Ground is 1, always so. All the ground links is 1.
They are at different height and like they are not in the same.
Doesn't matter. Ground is 1. Okay.
Okay.
You assume that there is a all-encompassing link, which is sort of grounded. Okay, it's everywhere and it's grounded. It's a bit like in electricity.
Okay. Okay.
Hocam, could you please show the joints again, the total joints?
Okay, the joints you mean? Okay.
Yes.
Okay, can you see my cursor?
Yes, hocam.
Okay, so this is 1, this is 2, this is 3, this is 4 and 5, because there are multiple joints here, right? This is 6, this is 7, this is 8, this is 9. These are all revolute now. And there is the prismatic joint on the ground. So 1 prismatic, so 10 joints.
Thank you hocam. Thank you so much.
And each of them have a Fi of 1. Degree of freedom of each joint is 1. So we just substitute this into our equation. 3 times L minus J minus 1. 3 times 8 minus 10 minus 1. So what does this make? Minus 9, right? 8 minus 10 is minus 2. Minus 1 is minus 3. 3 times minus 3 is minus 9. Plus the degree of freedom is 10. So we get 1. So this mechanism has a degree of freedom of 1. If you rotate this omega, if you rotate this small crank with an omega, the whole mechanism moves with a prescribed motion.
Hocam, I have a question.
Yes.
Hocam, how can we distinguish whether a system is in spatial space or not?
Well, if it's in the plane, I don't know. It's, you know, what you mean is we always drive everything on the plane, right? That's why you have difficulty.
Yes, hocam,
But
and
the
then we
way
take
it is
lambda always
traveled,
as 3.
usually you would understand whether it is in the plane or in the space. For example, if you have spherical joints, you are in this 3-dimensional space. But if you have a real mechanism, you would easily understand it. But on the drawing, it might be a little bit difficult, but usually it's not that difficult. You can understand it. For example, it's clear that this is in the plane. Okay.
Hocam, will we see any examples that are in the spatial space?
Yes. Well, we will see examples where we determine the degree of freedom, but we are not going to analyze spatial mechanisms like position, velocity, acceleration. They are much harder to analyze. So these are for graduate classes, not here.
All right,
Okay.
thanks a lot, hocam.
Okay, you are welcome. Now let me do these examples and then I will take a break. These are interesting, very simple, but then it will help you understand a few things. Let's say that you have a ternary link like this, okay? Which means that you have a triangle connected by revolute joints. You have 3 links here, and one is the ground, and we connect all these 3 links to each other, and then we connect it to the ground. What do you expect? Actually, since we have put lines on it, you expect this to be act like a rigid body, which it does. Actually, this thing is simply acts like a rigid body, like here. And we will find the degree of freedom of it. You have 4 links, including the ground. You have 4 joints, 1, 2, what is that? Here you have 2 joints, that's the tricky thing. You see 2 and 4 are connected, and 1 and 2 is connected, let's say, okay? So you have 2 joints here, 1 joint here, 1 joint here. So J is 4. Each link, each joint has 1 degree of freedom. So you enter this to our equation, you find that this has a degree of freedom of 1, which means that this triangular link acts like a single link, and actually it is. All these joints mean nothing, doesn't mean that it moves. This triangle is rigid by itself. It doesn't move at all, okay? Okay. Whereas here, if you have this link now, if you ground it, what happens? Now something interesting happens here. If you have grounded the link 1 now, it is the ground now. So 1, 2, 3, you have 3 links. How many joins do you have? 1, 2, 3 now. Okay, it's not 4 anymore. Again, each joint has a degree of freedom of 1. If you find the degree of freedom, you find that it has a degree of freedom of 0. Now this is grounded. It means it doesn't move. It is a structure, as I have said. And obviously, you can see that it's a structure. If you apply a force on it, it doesn't move.
Hocam,
Yes,
may you explain why it is 4 in the first one?
the number of joints.
Yes, hocam.
Okay, these are clear. These are one joint. The thing that is tricky is here, right? Here
Yes.
you have 2 joints. One joint is between 2 and 4, right?
Yes, hocam.
And then that is connected with the ground link. So with the ground, you have a connection joint that is, let's say, between 2 and 1. So you have 2 joints here at this point. So you have, if you want, let me, how do I write it? One R here, another R here, but you have a 2 R here.
So
That's
it is, isn't it the same for the second example also?
No, but because this first one is grounded already. So actually, the first link is in the ground. This is also the ground. Okay. So here you have a joint between 1 and 2 only. Here you have a joint between 1 and 3. And here you have a joint between 2 and 3. Clear? Think about it.
In this example, we don't count the ground link because we said we have 3 links. So the one is
Well, this is also ground. The one is grounded already. Okay, one is
okay. So we take the one as a like totally as a ground.
yes.
Okay.
Because both parts of it is grounded, so it is grounded.
Yes. Okay.
Okay. Another thing is the gear pair. We said that the gear pair has a degree of freedom of 2, right? And let's see, we have 2 gears, 1 gear here, 2 gear, second gear here. We connect them with 2 revolute joints. The number of links, 1 is the ground, 2 is the second gear, 3 is the 2 is the first gear, 3 is the second gear. So L is 3. J is 3. What are they? 2 revolute joints. And there is a gear pair here, gear joint. And the gear joint has a degree of freedom of, remember, 2. So sigma Fi is it's here. 1 plus 1 plus 2 is 4. This is for the gear joint. 2 is for the gear joint. And we find that F is equal to 3 minus 1 plus 4. 3 minus 3 is here. Minus 1 is, this gives you a minus 3. Plus 4 is 1. Now, 2 gears that are connected with revolute joints, this mechanism has a degree of freedom of 1 as expected. But the gear pair itself has a degree of freedom of 2. Okay, just the gears without the revolute joints on these sides. The gear pair has a degree of freedom of 2. Okay, that is, it constrains only 1 degree of freedom by itself without the 2 revolute joints next to them. This helps you explain why we introduce the gear pair introduces the gear pair or the gear joint has a degree of freedom of 2. Okay. Any questions up to here?
Can you please explain again why the gear joint has a degree of freedom of 2?
Well, this is what we had defined as before. If you remember, in the previous slides, we said that gears and cams have a degree of freedom of, as joints have a degree of freedom of 2, because they allow translation with respect to each other and rotation. Gears by themselves, without, without these revolute joints. So,
Thank you, Hojam.
okay. So if you connect them with revolute joints and mesh them to each other like this, you see that the gear pair as a mechanism has a degree of freedom of 1, which we expect actually. The degree of freedom of the gear mechanism and the gear joint are different. That's what I try to say here.
Hocam,
Yes.
how does a gear joint allow for translational motion? Could you please explain?
Okay, let me go back to, it was here. The gears have sliding and rotation motion between 2 teeth. If you have 2 teeth here, okay, there is a possibility of sliding motion that is between these two gears. There is possibility of sliding and there is the possibility of rotation. So 2 motions are possible. But if you connect them to each other, as I have done in this example, okay, as a mechanism, this thing with 2 revolute joints, the gears, the 2 gear mechanism has a degree of freedom of 1. But
Hocam, but
gears,
aren't the sliding and the rotation dependent on each other?
well, if they are not constrained with those 2 revolute joints, no. You see, it is the revolute joints that make the trick, that make them sort of dependent on each other. If the gears are loose, no, they don't constrain.
Okay, so without the revolute joints, could like the gears like do this kind of motion, like where they
Yes,
slide sideways?
without the revolute joints, gear can do that motion,
Okay,
sliding and rotation.
so it's a sideways sliding.
Yes. Yes.
Okay,
Yeah,
okay,
that's
thank you,
what
Hocam.
it is. Okay. All right, so we have come to where? Here. So I think we have done enough here. So let's take a break at this point. Let me stop recording.